section left in this chapter, and that's it. I feel like we just started this one. One section left, okay? Before we do the actual section that goes along with this, which I think is like 9-6 or something, 9-6, we're going to do intro to the next section, solving these guys. And these are a lot of mixture problems, distance problems. You are not listening and you need to be quiet. You are going to be lost, okay? All right, on the front side here, mixture problems. There are two different types of mixture problems. I am going to do this first one with you, and then number 1 is homework. Do you see that? Okay, this is how this works. I do one with you and one for homework. They are very similar. If you do not listen for the top one that I do, you will be lost. The distance problem. There is one that we will do together. Number 2 will be for homework. Do you see how that works?
Yes.
Okay. And then we have work problems. So I'm going to do this one with you, and then I'm going to give you the numbers that you need, and you're going to find partners and stuff to do the work problems on the back side. I'll explain that when we get to it. Here we go. Number 1. Well, before number 1, the intro to mixture problems. Here's how this works. You guys have seen these problems probably before. I'm going to show you how this is like idiot proof. It's like writing the equation out, figuring out what you need to add, blah, blah, blah. So you've seen problems like this before. How much? It said it's idiot proof. That means everybody can do it. Okay? I didn't say who the idiots were, all right? How much of a 70% acid solution should we add to a 15% solution to raise it to 60%? So, don't write this down, but here's what we have going on here. I have something that is 12% acid, not very strong, not very acidic. And what I'm doing is I am pouring into that 70% acidic solution so I can raise this 12% to a 60%. I want this to now become 60% acid solution, right? I'm going to have to pour quite a bit of the 70% in there, right? Sorry, not 12, 15. I'm looking at 12 milliliters, okay? So that's what I have going on here. I'm pouring the 70% into the 15%, and I want it to become 60. Got it? I'm going to have to pour quite a bit in there, all right? So here's the deal. I have things that I'm adding together. So I have my first solution plus what I'm adding, and I have what it needs to come out to be. Write this down. My first solution, what I'm adding to it, has to come out to be the ending solution, okay? And the way that this works is that I have the amount times the concentration, okay? C-O-N-C, amount. I'll just do amount times concentration, amount times concentration. So I'm taking some amount times the concentration of that amount plus another amount times the concentration of that amount, and I want it to come out to be the final amount times the concentration of that amount. Got it? Okay, let's write down what we know. I know that I am adding 70% acid solution. I am adding my 70%, so I'm going to put 0.7 in the concentration for the second one. Got it? 70% is 0.7, true? I don't know how much I'm adding, so I'm going to say X is the amount, right? X is my variable. I don't know how much I'm adding. That's what we're trying to solve for, okay? How much should we add to a 15% solution? Where does the 15% go? Concentration of the first one, that's 0.15, concentration, okay? Now, how much do we have of that 15%? That's my amount. That is 12, right? And I want the outcome to be 60% concentration. Now, what is the amount going to be at the end? I don't know how much it's going to be at the end, right? But what I'm doing is I am taking 12, and let's say I were to add 10 milliliters, right? What would I end up with? 22, right? Okay, but I don't know I'm adding 10. I know I'm adding X amount. So what am I going to end up with for my final amount? Yeah, 12 plus X. Guess and check is going to be like really a long process because these may not come out as whole numbers and you'll have to check a bunch of decimals. Sure, you're going to be there forever, okay? So do you see why the amount is 12 plus X? We don't know how much we're adding, but our final amount is going to be 12 plus X. Got it? Okay, let's just solve here. Let's do this part. Can I take 12 times 0.15? Yes. Sure I can. What is it?
Good question.
9.
No, I bet it's point something.
Not right. What?
1.8.
1.8.
Yeah.
I wanted to say 0.9, but 1.8. Okay. Plus, what's X times 0.7? 0.7x. Okay, so I've got these two pieces on this side. I've condensed them. I've gotten rid of some parentheses. What do I do with this right side here?
Hey, I can't see.
What?
I can't see.
Oh, you can't see? I'm sorry.
0.7x.
I'm going to distribute. I'm going to like back distribute, right? The 0.6, if it was in front, you would distribute it, right? What's 0.6 times 12? 7.2. What's 0.6 times x?
0.6x.
Okay, now we're going to solve.
Divide by, no.
What should we do? I've got an x here and I've got an x here.
Subtract the 0.6. Yes.
Now, by the way, hold up. By the way, hold up. Who hates decimals?
Me.
Like, we would rather have whole numbers, right?
Yeah.
Each one of these has one decimal place. Did you know that you can multiply the whole thing all the way through by 10 and get 18 plus 7x equals 72 plus 6x? Did you know you could do that? Because you're moving the decimal on each one place. Did you know that you could do that? Okay, so now this is just an algebra problem. What are you going to move there?
Subtract the 6 and
Minus 6x minus 6x, okay? Let's subtract the 18 over. Can I do that at the same step? Is that confusing?
yeah,
7x minus 6x is
1x.
1x, or just x. 72 minus 18 is 54. What does that mean?
X equals
X
54.
equals 50.
I have to add in, is this milliliters? Yeah. I have to add in 54 milliliters. But keep in mind, I'm starting with 15 and I'm adding 70% and I want to raise it up to 60. I'm going to have to add in a lot, right? 12 milliliters is what I have to start with. I'm going to have to add 54 more in order to be a 60% solution.
Wait,
Yeah?
Wouldn't it be 5.4?
No.
No.
No. No. Oh, because you multiply
Yeah.
by 10?
Yeah.
Okay, when you multiply by 10, like it, because I'm doing it to both sides of the equal sign, I don't have to divide by 10. Like, think of it this way. Like, let's say I have,
Well, think about it this way.
like, half of x equals 4, right? Half of what number gives me
It'd be like point x.
8, right? X would be 8 in this case, right? I know that x would be 8. So if I multiply this by 2, right?
This is coming to your.
X would be, x equals 8,
Couldn't
right?
you
I don't
also-
have to
yeah.
then just divide by 2 to get the actual answer,
Couldn't
right?
you also think of it if it came out like point x equals 5.4 is what it would come out.
Right,
to.
right,
You still have to
right.
multiply.
So like point, yeah, because it would have been, if we would have done this the regular way, I would take, and subtract 0.6, so this would have been 0.1x equals 5.4, and I divide
Yeah.
by 0.1, which is 54. Yeah, good question, I'm glad
Bad
you do that.
question.
Okay, good?
You asked
All right.
But you're not right.
Okay, let's talk distance. Here we go. Okay, I want you to write something down up above where it says distance. We're going down to this distance problem. You guys have to do number 1 on your own. Set it up exactly the same as what we did up here, but let's do distance. Number 1, here we go. This is a little bit harder. This is a little bit harder, so here we go. Write this down. Distance equals rate times time. Have you seen that before? Distance equals rate times time. If I am going 60 miles an hour for 3 hours, I have gone a distance of 180. That's my distance, right? Distance equals rate times time, approximately. You know, excluding like stops and things like that, whatever, right? If you're constantly going 60 miles an hour for 3 hours, exactly, you will go 180 miles, approximately, right?
3,000.
Okay, so distance equals rate times time. Okay, here we go. Sandra's canoeing rate in still water is 6 miles per hour. It takes 3 hours to travel 10 miles round trip. Assuming a constant rate of speed, determine the rate of the current. Okay, here we go. I don't necessarily know 10 miles round trip. Okay, here's what, don't write this down, but I'm going to show you how this works, right? She's going and then she's coming back, okay? One thing that I know is that the distance going this direction is going to be the distance coming back this direction, true? Okay? What I don't know, if it takes me 3 hours to do both, I don't necessarily know that I'm going 1.5 hours this direction and 1.5 hours this direction. True? If I'm going with the current, I might be going 1 hour, right? And if I'm going against the current, it might take me 2 hours to get back, right? So I know that the distances are going to be the same, but I don't necessarily know that the time it takes is going to be the same, right? Okay? She's rowing at a constant speed. So like she's rowing, rowing, rowing. But sometimes it's going to feel faster that she's rowing because she's going with the current.
I thought it says that she's constant rate of speed, so like not.
No, it says
She is rowing at a constant rate of speed.
no. It says like
Right?
her canoeing rate is
Assuming a constant rate of speed that she is canoeing. So if she is canoeing 5 miles per hour, I have no idea how. If she is canoeing 5 miles per hour and the current is 6 miles per hour. When she's going with the current, it's going to feel like 11. When she's going against the current, she's only going 1 mile per hour. Does that make sense? Okay? So that's how this works.
6 miles an hour. She's going 5 miles an hour.
She'd be going -1 miles an hour.
Yeah, in still water, Sarah's canoeing rate in still water is 6 miles per hour. So her, okay. Oh, determine the rate of the current. We're trying to find the rate of the current, not her rate. We know her rate. So we don't know the rate of the current. We don't know the current's rate, but we know that she is going a constant 6 miles an hour. Okay, here we go. Let's set this up, all right? So the deal here is, we're talking about time, okay? What I'm going to do is, the only thing that I know, really, is time, the time that it takes going and coming back, okay? Now, if I solve for time, are you guys watching?
I am.
If I solve for time, I can get rid of the rate by dividing by the rate. Yes?
Yeah.
Time is equal to distance divided by rate. Yes? Okay. So the time, I'm going to say the time going plus the time coming back. I'm going to say back is equal to how much? The time going, the time coming back is equal to 3 hours. Now, we don't necessarily know that going and coming back are the same rate, like 1.5, right? That's not 1.5 going, not 1.5 coming back, but we know that it's 3 no matter what. So 3 no matter what. The time going is distance divided by rate, plus the distance divided by rate. Distance divided by rate, distance divided by rate. All right, the distance. If we're going 10 miles round trip, how far is it going and how far is it coming back? 5. That should be the same, right? 5 going and 5 coming back. So my distances are the same. She is canoeing at 6 miles an hour. But if we're going with the current, it's going to feel like I'm adding X number of hours onto my current, right? But if I'm coming back, it's going to feel like I'm subtracting that, right? Okay?
The distance again?
The distance, it says 10 miles round trip.
Oh.
And so going and coming back has to both be 5, right? Because we're doing the same, okay?
No, it could be like 7 G.
Yeah, but a round trip, if I take a round trip from here to Hastings, it's going to be the same distance going to Hastings as it is coming back from Hastings, right?
Not if the
Okay.
continent shifted.
Okay, but we're on the same continent, so it doesn't matter if the continents shift. If there's an earthquake that splits the ground in half between us and Hastings, all right, whatever.
Yeah.
Okay? All right, good? Are we ready for this? All right, so here's what we have. We got to figure out how we're going to do this. What?
What's the velocity of the wind?
The current of the river takes the velocity of the wind into consideration already. So we don't have to deal with it.
What? That's
Right?
So if
Sure, yeah. Yeah,
the rivers don't always flow the same way as the wind.
true, but it does take it into consideration though.
Not really.
If you have a river that's like going from north to south and you have a southeast wind, you're going to go with the current probably, or like it's
Yeah,
going to
but
push it further.
If you're going, like, if the wind's blowing this way at you 5,000 miles an hour, the current's going 1 mile an hour that way, are you going to be going just as fast as if the wind was going 5,000 miles an hour that way?
so much
The current be going 1 mile an hour that way?
No,
Yeah, so it does.
I don't know. Whatever. Okay. All right, so we're here now. We have our equation established. Whatever. Your equation for number 2 is going to look similar to this. I don't know what else to tell you. Okay, now we got to solve the thing. Ugh.
I don't have enough.
I know you don't have enough room. I'm going to write it right under here. Okay? Here we go. Boys, stop with the coins. Or Simon. 3 as a fraction is 3 over 1.
Why are you putting that?
3 as a fraction is 3 over 1. I have to, when I'm adding rational expressions, I have to find a common denominator.
Why are we overlapping?
6 plus x and 6 minus x.
Yeah, no, wait. Why did I
6 plus, no, they don't cancel out.
Just kidding.
I didn't make those sounds.
Can't you just take it times the
You have to do
negative
like
x?
35
Give me the coins!
I don't want the coin.
Okay. All right, identify a common denominator. 6 plus x and 6 minus x are not the same thing. So I have to have a common denominator of
You don't got
6 plus x times 6 minus
I'm
x.
just putting that as junk underneath.
And 6 plus x, you can do that. If you want to do scribbles underneath, that's fine. 6 plus x, 6 minus x. Okay, shh. What? Hey, in the middle of my desk. Okay, so that's my common denominator. This is exactly what we were doing before, right? Okay, so I have a 5 here, and I have a 5 here, and I have a 3 here. So now we have to multiply by what they need. So take a look at this first 5. He has 6 plus x below him, right here. This guy, 6 plus x, what is he missing? 6 minus x, okay? The second 5, he has 6 minus x below him, what is he missing? 6 plus x. What's the 3 missing?
I tried paying attention.
Shh, shh. Okay, there's those two. All right, now, are you ready? This is my favorite part of the whole thing. Because we have an equal sign. Because we have an equal sign, the bottom goes away. It's gone. Yay, right? The bottom goes away. Do you want me to show you why? Hold on. You want me to show you why? Okay, let's say I have x over 6 equals 1 over 6. Let's say x over 6 equals 1 over 6. What's x equal to? 1. X is equal to 1, right? So my bottoms are gone. Okay, so that's how that works. The bottom goes away as if you have an equal sign. All right, now let's solve some stuff. I'm going to put it up over here. Distribute the 5 through. What's 5 times 6? 30 minus 5x. Okay, 5 times 6 again. Okay, Dylan, I don't care if you pay attention, but you're not going to distract other people, so be quiet.
Yeah, Dylan.
Okay, plus 5 times 6, 5 times x.
You know, it's hard for
30. 30 plus 5x
When you're being disrupted,
is equal to.
it's hard to listen.
Okay, shh. Let's FOIL the 6 plus x and 6 minus x out real quick. Don't write that down. 6 plus x times 6 minus x. 36.
Wait, why can't you just like separately foil the 3 with each one?
6x. You can, but then you have to put them
You can, but you only want to multiply the 3 through one of them and not both of them. Because then you're multiplying by 9 instead of multiplying by 3.
Yeah.
Yes.
Obviously,
I would rather FOIL them first and then multiply by 3. Because I'll show you why here in a second. Minus 6x, oop, plus 6x minus x squared. What happens in the middle? Cancels. So now this is 36 minus x squared. Shh. Boys, this is a difference of squares like in reverse. Okay, now multiply by 3. 3 times 36 minus 3 times, or times 3 times negative x squared.
Can't you cancel the 5x and something just go away? Plus 5x minus 5x?
Yes, they will.
Right?
3 times 36 and 3 times negative x. It's what? What?
112.
It is 102. No, 108. 108. 108 minus 3x squared. Okay, we're getting closer. Now we're to this point because my bottom is gone. Can the 5x's go away? It is torture. It's awful. 60 equals 108 minus 3x squared. Okay, we're almost there.
subtract
I
1.
didn't take times 3.
Minus 108.
Hate this stupid math.
Negative 3x squared equals negative 48. And then divide by negative 3. X squared equals
36.
16.
No, that's
48 divided by negative 3 is 16.
Yep.
And then we take the square root.
4.
Is 4. What did we just find?
You've got to be kidding me.
The rate.
Current.
The rate of the current.
Miles per hour.
The rate of the current.
I don't like that. I don't like
Awful.
that either.
Awful. That's a
That's a lot of
lot.
stupidity.
It's a lot. It's a lot. Okay. Let's.
All that for x equals
Woo! All that for x equals 4. I'm almost wondering if Jacob's guess and test would work better on this problem. But we don't necessarily know it's gonna come out as a whole number. That was super nice of
You
them.
know, if it was 4,
Like the numbers, like in the table, it goes 3, 4, 5, 6. Just to let you know if you were curious.
Yeah.
Also, instead of doing all the
I love it.
What?
instead of doing all the common denominator
So
stuff,
welcome,
couldn't you just
Lauren.
multiply both sides by like what's on the bottom of each of the fractions?
yes,
And
you
skip
could.
that part?
Right.
What are we talking about here?
Like instead of doing all the common denominator stuff, you just like multiply by 6 plus r, 6 minus r.
Do you know that problem?
Yeah.
Is that just finding a common denominator?
Yeah, that's basically like finding a common denominator.
And you all like write it out loud.
Right,
and stuff.
right.
I didn't
Waste
write
of time.
Okay, let's stop there. You guys do 1 and 2. That's all you need to do. 1 and 2. Try to get through those 2. Work on them right now with the information that you have. Okay? If you need to make a table like what they have there, go for it.
Jacob,
Yes, I
I'm gonna
did.
try your guess.
I'll send it. Yes.
Okay.
Yep. I gotta send it here. Yeah. Yeah. Yeah.
Do you blame
Yep.
me?
Yep.
Not really.
All right. There you go.